Good afternoon, class, or good morning, whatever time it happens to be when you are watching this video. So, for today, our goal is to finish up Chapter 3 and go ahead and get into this final section for Section 3.5. So, what are we going to be talking about here today? Well, in Section 3.5, we start to talk about what are absolute max and minimums. We're talking about where do we have these maximums and minimums that are the largest or are the smallest values over the entire function, the entire graph. And we'll talk about what that looks like, how to find them, how to calculate them. But as we go into this, you're going to find that this is very closely related to our definitions for local minimum and local maximum. So we'll talk about that and clarify the difference between the two because they are not the same thing. Sometimes you can have an absolute max that is also a local max. Well, that's going to happen for every absolute max, but not every local max is a absolute max. And we'll talk about that. So, as an analogy, it's kind of like the square rectangle thing. All squares are rectangles, but not all rectangles are squares. And that relates directly to absolute max and local max. But we'll get into that. We'll talk about it. All right. So let's go ahead and get started. We are in section 3.5. So I'm just going to start by going ahead and giving you guys these definitions, and then we'll take the chance to talk about them a little bit. So, if is the domain. Oh, hold on. I see the textbook's got a misprint here. Yeah, we'll fix that. Yeah. Okay. So we start with assuming right, we have a function with domain we can access. All right, sorry about that. The definition was written kind of strangely here in the textbook. So what are we talking about? So if, and of course my marker is dying on me right as I start this. Apologize for that. All right, so if C is, wow, cannot write, is in the domain of F, sorry, of F. If C is in the domain of F, so we're picking a particular X, we can call it C. So if C is in the domain of F, and this following statement holds for all X in the domain, and this following statement holds for all X in the domain. So what following statement? Well, if f of x is less than or equal to f of c, so we're looking at the y values. If for all of the other x's in the domain, the f of x is less than or equal to the f of c, then we say that f of c is a absolute maximum. So in other words, we have this y value that is the biggest for the entire function. There's no other y values that are bigger, and so we call it the absolute maximum. So what does that look like? Well, think about the graph f of x is equal to negative x squared. Well, that's not too bad to draw. We know it looks like that, just our basic upside down parabola. But what do we have here? Well, if you consider when c equals 0, then that's the very tippy top of this upside down parabola before it zooms off to negative infinity in either direction. But what do we have? This is the biggest point, it's the highest point that this graph ever reaches, and then it goes down forever. So this is a absolute maximum. Well, by the same definition, if we then flip it, if f of x instead is greater than or equal to, so for all x, all the x values, the y is larger than the y value for f of c, then f of c is a absolute minimum. And again, to take the same kind of example, if we have a function that is f of x equal to x squared, then that's our normal parabola that's facing upwards. And here we have a absolute minimum at c equals 0 because it is the lowest point that is ever reached by this function before it starts going back up towards positive infinity. So this is absolute maximum and absolute minimum. So how does this relate to local max and min? Well, as you may recall, what is a local max or a local min? A local extrema occurs where we have critical points. So if we don't have critical points, we don't have local extrema. Well, take a look here at these two examples. If we think about what is the derivative, well, up here, f prime of x is equal to negative 2x. Down here, f prime of x is equal to 2x. In either case, it has a critical point at x equals 0. So what else does that tell us? Well, that tells us these points where we have absolute maximum and absolute minimum, they're also critical points. But even more than that, we also know that based on our definition for local extrema, if we use the first derivative test, we can look at, okay, what's going on here? If we test values to the left of 0, then let's say negative 1. So f prime of negative 1, we'll get a positive number. And this is for our top example. And if we test the other side, so f prime of 1, then we get a negative number. Well, that's the same thing for what we need to have a local maximum. So an absolute maximum is also a local maximum. Same thing down here, an absolute minimum is also a local minimum. So this is great. We know a little bit more about what these values are. They have to be these local maxima or local minima, but the reverse is not necessarily true. And I'll give you an example here. Suppose we have a graph that looks something like this. Well, then right here, we've got a point where the slope is increasing, increasing, increasing. It flattens out. So the slope is 0 here. That's a critical point. And if we check our derivatives, so if we do the derivative test, the first derivative test on both sides of this point, we have that it's increasing to the left and then it's decreasing to the right. So this is a local maximum. But is it the maximum everywhere on this function, everywhere on this graph? Well, if we look over here to the right, you can see that the graph zooms off to infinity here on the right side. So right there, I can already pick a point that's higher than this point. So it is not a absolute maximum. So this just goes to show that local minima and local maximum are not necessarily absolute maximum and minimum, but the reverse is true. An absolute max is a local max. An absolute minimum is a local minimum. It's an important distinction, and you want to make sure you keep them separated, because sometimes you'll have a question that asks you to find one or the other, and so you have to know the difference between the two. It becomes very important. All right, great. So let's keep going then. So we've talked about, as far as defining them, what they are, but now we'd like to go a little more in detail on how do we find them without just having a simple picture. Because when you have a graph, oftentimes it's very easy to pick out, which isn't a bad idea if you want to double check your work and make sure you get an answer that makes sense. If you graph it, then you should be able to see that, yes, it is indeed the biggest y value that the graph ever reaches. So it's a good way to test the answers you have and make sure it does add up. So what are we talking about next? Well, we have this interesting if statement, which I don't believe you're going to be... I don't believe you'll be specifically tested on this, but it is a nifty little thing to notice that can be helpful sometimes. So what do we have here? So we have the statement. If f is continuous. Now recall, what does that mean? That means you can draw the graph continually without lifting up your pen or your pencil. It also means that the limit exists for all values of x in the function. So from both sides, for any point, the limit always meets where it's supposed to. And not only does it meet where it's supposed to, it meets at f of x. So this is good. So we have something that is continuous on an interval AB. More specifically, this is on a closed interval. So we're including A and B in the domain here. So if f is a continuous function on AB, then f will have absolute extrema on this closed interval A to B. What do I mean by that? Well, take a graph, and it can really be any graph, even like this guy that we had from before. But if I restrict this to, let's say, this interval from A over here to B over here, so I only care about the graph between these 2 points, then I don't care about what I have to the left, so I'll just erase that bit up until this A. And the same on the right side. I'll erase this until we get to B there. And so now we're just looking at this restricted part of this graph. And note that it is also continuous. It doesn't have any points of discontinuity or breaks anywhere. So this statement says that if we have a continuous function on some closed interval, like we do here, then we will have absolute extrema. Why? Well, because it's closed and it's bounded, this can't zoom off to infinity anywhere. The limit has to exist. And because the limit exists at every possible point, then we have to have some absolute maximum. We have to have some absolute minimum. Why? Well, because it's bounded. It can't go off to positive infinity. Otherwise, it would have a point of discontinuity. And because none of these points zoom off to infinity in any direction, then there must be some biggest point. And that's what this statement is saying here. And if we look, we can clearly see that, yes, there's a maximum here, and there's a minimum here. And in this case, because we now have it bounded on the left and right, these are then the absolute max and min. So it's important to note that when you have these bounds here and it is continuous, then you're guaranteed to have these absolute extrema, and you should be able to find them. Now, the one pitfall to watch yourself with is that just because you have points that are local extrema, so we have a local max and a local min, then that local max and min might not be the absolute maximum. You still want to test your bounds. What's an example of that? Well, again, think about, let's see, let me give you a good example. Let's see. Think about the case where, let's see, actually, give me just a moment to pick out a good example and then we'll talk about it. And we're back. All right, so yeah, so here's actually exactly the kind of example we want to talk about here. So, suppose f of x is equal to x cubed plus 3x squared. But, more specifically, let's suppose that we have our graph bounded on -3 to 5, and this is a hard bracket on the right side. So we're including -3 and 5 in our domain. So what does this mean? Well, and we can check this as we plug stuff in, but what does this graph look like? Well, if we check f of -3, then this is -3 cubed is -9, and then -3 squared, or sorry, this is 27, -27. And then if we have -3 squared, that's 9, times 3 is a positive 27. This is 0. So at -3, we have the point 0. We also have another point at 0 for f of 0, right? If I plug in 0 for x, then all I can get is 0. So I got another point here. Well, you can keep plugging in values, or you can graph it in a calculator or in Desmos. Either way, it's going to look something like this. And then we got a 5 out here. Oops. Yeah, we got a 5 out here. So I've cut off the function. Now, ordinarily, this would keep zooming off there, and this would keep zooming off down here. But I've bounded it. Why? Because this goes along with our statement, this if-then statement we have over here. So what is the point of this? Well, let's suppose we wanted to calculate absolute max and min. Then we would need to find our critical points, but as you'll see in this example, we also have to check our bounds. So let's give it a go. So what's f prime of x, since that's what we need for critical points? So we're going to take the first derivative, and we're going to have 3x squared plus 6x, just using the good old power rule from before. So now we have this, and I want to set this equal to 0. So I'm going to factor out a 3x. So I'm going to have 3x times x plus 2. Okay, great. So what do I have? Well, this is equal to 0 when x equals 0 or -2. And looking at our picture, that adds up. We got -2 here with this slope of 0 up here. And then at 0, we also have this another slope of 0 here where it flattens out at the x-axis there in the middle. Okay, great. So what? Well, by the first derivative test, we already know that by plugging in values in between, we can test to see is this a local max or a local min, so on and so forth. Well, if I plug in f prime of -1, f prime of -1, so -1 squared, that's going to be 1, times 3 is 3, but then -6, so 3 minus 6, I'm going to have a negative number here. If I plug in +1, well, that's going to be positive. If I plug in -3, well, -3 squared is 9, times 3 is 27, 3 times 6 is 18, so 27 minus 18, I actually get a positive 9, so I'm positive on this side. So what does that tell us? That tells us -2 is a local max, and x equals 0 is a local min. But in order to find our absolute max and min, we also need to check our bounds. Why? Well, let's take a look. So if this is my local max, then f of -2 would have to be the biggest value I could ever reach for this function in between these bounds of -3 and 5. But as you can see, when I plug in -2, so going back to f up here, -2 cubed is -8, and then -2 squared is 4. 4 times 3 is 12, so plus 12. 12 minus 8 is 4. So that would say my absolute maximum occurs with the y value of 4. Well, what if we check our bounds here? What about 5? So f of 5 is equal to 5 cubed. Well, that's 5 times 5 is 25. Times 5, that's going to be 125. Then I'm going to have 5 squared, so 5 squared is 25. Times 3 is 75. And 75 plus 125, we've got 200. Now the absolute max has to be the value that is bigger than everything else in the domain. Well, in this case, our absolute maximum actually occurs at 5. And so this is our local max. And for our local min, we already selected, so this is our absolute max right here. Absolute max. Now over here, when we were looking at our local min of 0, f of 0 equals 0. But if we look at f of -3, so that's our other bound on this left side, then f of -3, we're going to get 3 times 3 is 9, times 3 is 27, so we got a -27. And then when I plug in -3 over here, -3 squared is a positive 9. 9 times 3 is a positive 27. Then we get 0 again. And so in this case, we actually have two absolute min, and we have 2 points that are the smallest over this interval. There's nothing bigger than these two values, so they're equal to each other. So what's our absolute min here? Well, the absolute min is at x equals 0 or -3. We have two of x values that give you the absolute min. So there you have it. It's very important that when you're trying to find these absolute max and min, that you do look for where the local max and min, because those are candidates for being absolute maximums and minimums, but they might not necessarily, so you still want to check your bounds. Let's see, anything else to note about this? So it's also interesting that in this particular case, because we're talking about where we have a bounded domain, then this forces us into the situation where we could actually have an absolute max that is not a local max. So what I said earlier about absolute maximums always being local maximums, that's only true if we're talking about functions that are not over some bounded domain. In the case of a bounded domain, then you always have to check the bounds. But if I were dealing with any other function that is not bounded, like something like this, then the only way you can have an absolute max is if it's also locally a max in its area. So important distinction here. In the case of a bounded domain, your absolute extrema are not necessarily local extrema. But in the case where you have no bounded domain, then your absolute extrema are always local extrema. So it's important to keep track of the distinction there. All right, great. So what's next? Let's see, we've talked about our definitions. We've talked about the importance of continuity over a bounded domain. Now we're ready to talk about some other examples. Okay, so we have some business examples to go back to some of the stuff we've been looking at previously. So give me a chance to erase this real quick. All right. Okay. So what's the business example we want to look at? So, suppose you're told the weekly revenue from the production and sale of X units of oil. So maybe it's a barrel of oil. It doesn't specify what they mean by unit, so it could be a barrel, it could be a tanker, what have you. Whatever their measurement of unit is, all we need to know here is that for X units of oil that are sold, the revenue is given by. So in this case, they give us the revenue function, which is nice. That makes it easier on us. So revenue is given as 78x minus 3x squared. And then they also say, and this is for $1,000. So whatever answer we get, that's in thousands. So that's a good bit of money there. The cost function is given by c of x. So again, they give it to us, which is nice. C of x is equal to x squared plus 30x plus 7 plus 7. The cost function is given by c of x is equal to x squared plus 30x plus 7. Find the number of units of oil that are to be produced to maximize the profit if 0 is less than or equal to x less than or equal to 27. So this last statement here is important to note because this is indicating to us what is our bound. Now in the context of this question, why does a bound make sense? Well, producing a negative number of barrels doesn't really make sense. What does that mean to create -2 barrels? That doesn't really make sense. So we bound it by 0. Additionally, maybe there's some limit to how many you can manufacture in a day. Maybe your particular manufacturer can only produce 27 barrels for some reason. That's the most they can produce in a week. Okay, so we have this bound here and a little bit about, why a bound would make sense in this context. But now we're asked to find the number of units of oil, how many X can we produce so that we can maximize profit. So we're trying to find the absolute maximum for profit. But what is profit? P of X. Okay, there we go. That's what we're looking for. So how do we move forward? Well, we already know from previous lectures that profit is equal to revenue minus cost. Okay, so that's not too bad to do. Revenue is 78x minus 3x squared. Then we subtract cost. So remember to distribute your negative here. So we're going to have negative x squared minus 30. And you know what? I think I forgot an x up here. I did. Yeah, that should be minus 30x minus 7. Okay, so we'll just combine some like terms. negative 3x squared minus x squared, that's going to give us negative 4x squared. 78x minus 30x, that's going to give us positive 48x. And then we got our negative 7 here on the end. So there's our profit function, but now we're trying to find the absolute maximum. Now, because we're on a bounded domain for a continuous function, then we know the absolute maximum must exist. There must be some value of x that's going to maximize the profit over this interval. Okay, great. So what do? Well, we need to find our critical points because those are places that are candidates to be local extremum. And anytime you have a candidate for a local extrema, that is also a candidate for a absolute extrema. So we'll have to check that, check our critical points, but then we also want to make sure we don't forget to check our bounds because it's possible one of the bounds might be higher than one of the local extrema that we have. Okay, so let's do it. So p prime of x is equal to negative 8x plus 48. We set that equal to 0, and so I'm going to add the 8x over. We have 48 equals 8x. Divide by 8 and 45. 48 divided by 8 is 6. So this is a critical point. Okay, so that's a possible extrema, a possible maximum we want to check for. So we can do that. So, by our first derivative test, if I'm checking x equals 6 here, because this is where the first derivative was 0, now if I plug in numbers to the left, let's say 0, then f prime of 0 is, based off of this, positive. It equals 48. So that's positive. And if I plug in, say, 10 to my first derivative, then 10 times a negative 8 is negative 80. And so this is equal to negative 80 plus 48, but that's clearly negative. So we have here a local max. This is good because then that means that 6 is a possible absolute maximum. If it had been that this plus and minus were flipped and it were a local min, then we would automatically know it is not a possible candidate for the absolute max. And we would then just want to move on to checking our bounds. But in this case, it's a local max, so that's good. We haven't eliminated it as an option, and so we should still check it. So what's the last step here? Now we actually want to check what are the profit values and see what the maximum is. So we're going to have f of, I apologize. I should have been writing p instead of f. So all these f's here, that should be p. This is p prime. Apologies, but you get the idea. Right, so now we want to check what the actual profit values are. So we're going to have what is p of 6. So 6 squared is going to give us 36. And if we have 36 times a negative 4, then we've got negative 144. And then plus 48 times 6. So 48 times 6 is going to give us 288. And then lastly, we got a minus 7 on the end. So what do we have here? So 288 minus 144 minus 7, we get a final answer of 137. Now remember, this is in thousands. So 137,000 is the expected weekly profit if they sell 6 units, whatever a unit is. Okay, so not too bad. We still want to check our bounds. Now, if we think about, based off of our first derivative, we can actually save ourselves a lot of work here. What do I mean by that? Well, to the left of 6, we see that the function is always increasing. It was increasing as it approaches 6. So that means we've got, and I don't know what this graph looks like without graphing it, but that means I've got something that's going up and up and up and up to a point where it hits 6. Well, if I were increasing to 6, that means for every x value to the left of 6, my y value has to be lower, which further means 0 can't possibly be my absolute maximum, because by looking at the first derivative here, I know that f of 0 was increasing towards 6. So when we look at when x is 0, it has to be lower than f of 6. And so we already can eliminate it as an option, and we can save ourselves the time of trying to calculate for it. So now we only have one other candidate to check. And in fact, even in this case, we can already see by the same argument I just made that it can't possibly be correct. That 27 can't be the maximum. Why? Well, after 6, it's decreasing forever. The slope is going down, it's negative, it's decreasing. That means for every y value to the left of it, it must be the case that it's lower, it's smaller. And so just based off of this first derivative test I did here, we already know that 6 is our answer. But for the sake of argument, suppose that maybe you're working through a problem and you don't notice something like this. That's all right. You can still plug in the numbers and figure it out. So what's P of 0? Well, the profit, if we produce 0 units of oil, is 0 plus 0 minus 7. That's a negative 7. So obviously that's not bigger than 137. So we won't worry about that. And if I have a profit of 27, then what happens? Well, 27 squared is 729 times negative 4 is negative 2,916. And then we want to add 48 times 27. That's plus 1296. And then minus 7 on the end. You can already tell by looking at that, that's going to be some negative number, which again is clearly not bigger than 137. And so we're done. This is the absolute maximum in order to maximize the profit. So the company wants to produce 6 units of oil. And there you go. There's your final answer, and you're good to go. So we've talked about, well, the last couple examples have all been examples where we have a bounded domain. But for just a moment, I'd like to talk about, what about if the domain is not bounded? What if I want to find an absolute maximum or an absolute minimum over an entire graph, an entire function? Well, we can do that too. And in fact, like I discussed earlier, those are going to be at the points where we have local extrema. So it's going to be a similar kind of test. All right. So as a final example, consider when f of x is equal to negative x squared plus 2x plus 3. Now, if I graph that, we're going to have something like, well, at 0, we're going to have 3. So we got a point there. Let's see, where does this equal 0? Where does this equal 0? Well, if I multiply everybody by a negative, then I've got x squared minus 2x minus 3. That's going to be x plus 1 times a x minus 3. Yeah, that adds up. 1 times a negative 3 is negative 3. And a positive 1 minus 3 is a negative 2. So we've got these values where the function is 0 at -1 and 3. So here at 3 we got a point, and then here at -1 we got a point. And it's got to connect. So we've got, and again, this is just a rough sketch, but you can put it into a calculator or into Desmos and you'll see what it looks like. So it's something like this. And now we'd like to find what are the absolute extrema. Well, absolute extrema occur where we have critical points in the case of an unbounded domain. So let's go ahead and find our first derivative then. So f prime of x is equal to -2x plus 2. If I set that equal to 0, then I've got 2 is equal to 2x, and so x equals 1. So in fact, at x equals 1, so this picture's not quite right. If I had drawn it better. At -1, or I'm sorry, at +1, we have, let's see, that's a -1, plus 2 is 1, plus 3 is 4. So we've got a point like actually up here at 4. And so the picture looks more like something like that. At any rate, rough sketch, but you get the idea. So this is a critical point at 1 and a possible candidate for an absolute extrema. So how do we test it? Well, again, we use our first derivative test. So we plug in numbers to the left. I like using 0 because that's easy. 0 plus 2 is 2. It's positive on the left. For the right, if I pick 2, -2 times 2 is a -4, plus 2 is a -2, we're negative. That means this is a local max. But just like before in that last problem we talked about, I'm forever increasing from the left side. That means I'm increasing as I get closer and closer to 1. Everything to the left has to be smaller than it. But after 1, everything is decreasing forever. So for all the values to the right of it, it has to be lower than f of 1. And really, that's the same thing we get from the picture, except if you don't have the graph, then you can use this kind of test to figure out what we have. So, in this case, we have a absolute max at x equals 1 with a value of f of 1, which equals 4. We found that earlier. And then lastly, what about absolute min? Well, in this case, it doesn't exist. We don't have some value that's smaller than everything. Why? Because in either direction to the left and right, it's decreasing forever. It's going to negative infinity. So we don't have any absolute minimums, and we only have an absolute maximum. So that's what you do when you have the case where you're not given a bounded domain and you need to look over the entirety of your graph. So there you have it. Let's see, that pretty much covers everything I wanted to say today. Yeah, that's it. So quick recap, what are absolute and maximums and absolute minimums? They are the points on your graph that are bigger than every other value or smaller than every other value. They can be local maximums and minimums, but they're not always local max and minimum. And in those cases, you want to make sure that you check your bounds to double check that your bounds are not bigger or smaller than whatever value you're comparing it to. So there you go. That's everything for today. Of course, if you have any questions, concerns, by all means email me. Let me know if anything didn't make sense. We'll talk about it. We also have our Q&A later today, and of course, bring your questions there, and we'll go over it. So that's all I've got, and I wish you the best of luck.